Hello, my name's Stephen King with Undo, and joining me is Mohammed Al-Shahabi, a sales engineer for Undo. Today, we'd like to spend about an hour discussing Undo's LiveRecorder technology with you and the kind of results that we've achieved with telecom customers. So our agenda today will be a brief overview using PowerPoint slides, and then a demonstration run by Mohammed. One demonstration will get across some of the fundamental concepts of recording and replaying code, and the other will be a demonstration of how to resolve a defect within live telecom code. And then we'll discuss potential next steps with you. Undo's been working with major telecom customers in Silicon Valley to help them slash their MTTR, their mean time to resolution, of software defects. And that accelerates their delivery of new software components and also cuts development costs. How do we do that? Why don't we talk about the problem first? So when I first came to Undo about 2 years ago, I previously spent 7 years with IP Infusion working with a lot of the Valley's largest telecom customers, including IBM, Ciena, Brocade, Broadcom, multiple others. And I was really surprised to find that telecom customers are still shipping defects in their products. I always assumed that they wrung out every last defect before they shipped, and that's not today's reality. So what we've seen with our customers is every large complex code base has some latent defects, some which are known and some which are unknown. The defects are not necessarily a crash, so you're not necessarily going to see a core dump as a result of the misbehavior within the code. Oftentimes they're intermittent, and sometimes they present security vulnerabilities within the code. And getting after these is very, very difficult. And that's the other thing that we see is defects are very expensive to fix. Replicating them takes time and hardware, typically resources. The tools that we're still using remain primitive, printf, logging, core dumps being the primary ones. And it's a very iterative approach to trying to determine what went wrong with the code. Typically, engineers have to hypothesize what happened, given limited amounts of data, further instrument the code, restart, and wait longer until the next time the code fails to get any more information. And this can take quite a long time to solve defects. So what LiveRecorder does is fundamentally we record and then we replay and help customers resolve faster. How do we do that? Well, the recording piece is called LiveRecorder, and what it does is it records everything within a process or processes at runtime. That way, it produces a recording file that has an exact recording of the defect in action. Then, using our replay technology, typically with GDB or our logging technology that Mohammed will demonstrate, engineers can more efficiently approach both reproducing and solving the problem. And what it allows customers to do is resolve defects much, much faster. And we'll give some examples of that in a minute. LiveRecorder can help solve any class of defect. We've had customers successfully solve race conditions between multiple threads, interactions between processes, shared memory corruptions, stack overflows, literally every kind of defect imaginable. If it can be expressed in C or C++ code, we can help solve it. Why is LiveRecorder so powerful? Well, the first one is it records the software failure in the act. And a lot of people underestimate this particular feature. Once you've got the recording in hand, engineers and QA people don't have to spend time constantly reproducing the failure. Now they've got the bug and they can start over multiple times. They can go to the end or backwards, and it makes it much more efficient to solve the bug when you've got the actual failure and you don't have to keep waiting for it. On the replay side, as I alluded to, you can actually use GDB to debug it, both forward and from the end going backwards. We have other features such as post hoc logging that make it much more intuitive to capture the bug than looking at logs or core dumps. And the engineers can now focus on actually resolving the defect, asking themselves the question, where did the code go wrong, rather than where do I think it went wrong, and then putting in more logging and further waiting. So those are the ways in which LiveRecorder brings this power to developers, helping them to reduce their debug time. So I'm going to give a few examples of how our customers are using it today. This is our largest telecom customer. I can't say their name, but they are the largest in Silicon Valley. And when we went through the initial proof of concept phase with them, they actually gave us to debug some known bugs that they had regression tests for, and some bugs that they hadn't solved in this particular application. With the regression test, the solved bug that had a reproducer, we recorded that and gave it to one of our engineers. So this is an undo engineer that doesn't work for the customer, is not familiar with their code. And they actually took that, and by using our technology, we're able to resolve that defect successfully within 3 hours. They later told us this defect was so complex, it was a third order defect caused by an errant pointer originally. But it took them 5 years to solve it, because they only saw it about once a month, and because it was a third order defect, and the only tool they really had at their disposal was put in more logging, recompile, restart, and wait another month until they saw it again. Again, from 5 years to solving in 3 hours, and the customer did verify, yes, you solved it correctly. During that session, we actually helped them solve a couple of other defects that were, I guess, hadn't been resolved. And those two, we handed the recording off to one of our engineers, and they debugged those problems in about 3 hours. So we solved both previously solved defects far faster, and we solved some unresolved defects, not knowing the code, not working for the company. So that's one result that we've achieved with that telecom customer. I've been working with them as an actual customer now for well over a year. SAP, they've been a customer now for about 5 years. And the way SAP uses our technology is they always record in QA. So the way their process works in this graphic is they'll run their tests in the evening. And if something fails, they'll rerun the failed tests using recording mode, is what it's showing in the middle. And then the next morning, the engineers come in and they'll have recordings on their desk, and they can debug against those recordings and solve the problems far faster. So they've got everything to reproduce that bug at their fingertips and can just focus on solving the defects. This is Cadence, another customer of ours for about 5 years. And Cadence has been using our technology in the field. The problems in the EDA industry are interesting because their customers typically won't hand over their model of their chipset and say, hey, your simulation fails. Here's the model of our chipset. Can you please debug it? Typically, their engineers have to fly and go on site in their lab, which isn't on a network, and debug in their lab. And from talking to one of their engineers at Cadence, typically these problems take, with their simulator at least, about 3 weeks to solve being on site. Now what they can do is they can ask the customer to flip a switch. It'll produce a recording of that failed run, and then they can send that recording back to them. And back at the factory, the engineers can then focus on solving the bug. At another one of our EDA customers, their VP of engineering told us that their attitude about our technology is once they have a recording of the failure, it's a matter of hours before they'll be able to solve it. So again, from the typical 3 weeks down to just hours, and not having to fly engineers on site. So that's a huge benefit for our EDA customers. In general, our long-term customers use an internal metric of a 10 times reduction in debug time for the typical software defect. So that's, very, very good result. So what we'd like to do now is show you how LiveRecorder works. I'll turn it over to Mohammed at this point.
All right, thank you, Stephen. And I'll go screen and share with you a look at how recording works and how replay works. So we'll start off with recording. and we'll start off with the model used by many of our customers in test, for example, SAP. Recording is or our tool comes with two pieces, the recording engine and the replay engine. And the replay engine, as Stephen mentioned, is called UDB, and it's very similar to GDB. It basically navigates the recording. The recording is a binary or shared library that can be added into your application or just placed on the target machine where the application runs. And when your application runs, it will then record it. So it'll attach to a particular process and record what happens there. So for example, let's say I have some tests that run overnight. And when a test fails, the test farm will rerun those tests. And it will just rerun the failed tests, but this time it will enable recording. It will just flip the switch on. And if that's a simple, live record and pass the PID, or live record and pass the binary of the application. And when it reruns the failing tests, it will now capture a recording. In the case where a test failure is intermittent, so let's say it happens once every 100 times, it will keep rerunning that one test until it'll rerun it, up to 100 times, and then it'll capture a recording when it fails again. And it's basically trading QA engineer time for CPU time, which is a pretty good trade-off. Once the recording is captured, it will generate the artifact, and that'll be this undo file. And in this case, I can open the undo file. So I can save that file, and I'll open it using the UDB debugger. So undo, and there we go. So I'll use UDB. So if anyone's used GDB, this will look very familiar because it's basically GDB with some extensions to allow it to navigate a recording. So, for example, I can set a breakpoint on main. I can continue to main. I can do next. You can see the concept of time. If I do input time, I can see that I'm somewhere in the recorded range. I can go to the start of the recording and look at the time here. I can go to the end of the recording and look at the time here, and you'll see that I'm now in the end of the recorded range. You'll note that there was a sig trap over there, and in fact, if I go to any point in time and hit continue, it will run to the next signal. In this case, there's a sig abort at the end of the recording, and I can do a backtrace to show me my stack. I'm actually going to switch to something called TUI mode, which lets me see command line and source. So over here, first I'm going to backtrace again. I can see there's an assertion. So I'm going to go to that assertion in my recording, and I'm going to do it using a few similar to GDB commands. So I can do a reverse finish, and I'm going to hit that a couple times, and it'll take me here to my assertion. So I'm able to move around in my recording, so I can do reverse next. And that's because a recording captures everything that happens in this run, everything that happens in a particular run, down to the instruction level. So the recording has everything that happened, and it's then able to recreate the state of the program. There are some other technologies that allow you to capture the state of the program at every point in time and get a snapshot of it, basically, such as GDB reverse debugging. But that's very inefficient and not a real-world utility. In this case, we're able to capture particular events in the recording or while we're recording, and then we're able to recreate the state of the program. So when I've recreated the state of the program, I can move freely through it and examine the state of the program at any point in time. So I can look at memory as it changed. I can look at variables and see how they're changing. And that allows me, being able to see the state of the program at every point in time, allows me to debug things much more quickly. And I'll demonstrate that right here. So there was that assertion. I can actually see that assertion happens because square root cache is not equal to square root correct. So I'm just going to print my locals and see here, square root cache is 0, square root correct is 15. So it's some caching function. And I can see that cache calculate function up here. Square root cache comes from cache calculate. So I'm going to go back to cache calculate and see why cache calculate returned this value. So I will do a reverse next, shorthand rn, a couple times, and then I'm going to reverse step back into that function. So reverse step back into cache calculate. So I can see here that I'm now in cache calculate, and I can see root, and I can see where square root is set. So I want to query this variable and find out why it's returning that value. So if I was doing a typical debug and I had an idea of where the bad value was coming from, I could set a watch point on it. Obviously, there's a reason that GDB is not the most popular tool, or it's the most well used, but not the most well loved, because you could set a watch point and then you'd be coming from the front, and then you hit continue a billion times until you reach the point of interest. The neat thing about recordings is I can move pretty freely, so I can set this watch point over here, but I'm at the end of the recording. I'm at the point where the failure happens, so I can just reverse backwards to the last time that expression was evaluated, and that puts me at the point in time where things went wrong. So that's where the value gets set 0. So right here at this point in time, you can see that the time has moved. I'm now at some point in time in the recording range where things went wrong. And at this point, it just becomes really easy to see the problem. You can look at my locals again, see that square root equals 0. It comes from square root 2, which is some negative value, which is what caused it to be set as 0 and unsigned int. Why is it that strange value? Well, square root 2 comes from square root of number 2, which is -1. Number 2 is number -1. So if number is 0, let me confirm that, yes. So if number is ever 0, I end up with this failure. And there basically should have been a check over there to make sure that number was greater than 0. Basically, I figured out this bug in some code that the first time around I didn't know what the code was, but I was able to step backwards and figure out what went wrong by looking at what happened, rather than the typical guesswork that I need to do when I debug. And that's okay. Where could have things gone wrong? I understand my code. Let me think about what could have gone wrong. Here are the few options, and I have to check each one. In this case, I just look at what actually went wrong and step backwards from there and see what went wrong. Okay, so the next step over here is then to show you a real-world application. Although this is kind of a simplified bug from a real-world application, I'm going to show you a networking application. Okay, so let's take a look at the second example with BGPD open source cloud application. So let's take a look a bit under the hood of how I captured recording. So last time we kind of took a higher level view of what it would look like in a test farm. In this case, I'll show you how the recording actually happens. So we have a LiveRecord executable that can either be passed a binary to run. So you can say LiveRecord my application, and when your application starts, it will record from start time until you stop recording, which can be done with passing a signal. The other way is to pass it in PID. So if you have a running daemon and you want to record it, you can basically say LiveRecord PID, pass it the PID of the process, and then you'll start recording, and then you can, again, Control-C, and it'll save out the recording file. It will automatically save out a recording file if a terminal failure happens. So if the process crashes, for example, it will save out a recording. And then there's finally an API, which can be used to record from within the application code. So you can use the undo API to start, stop, save recordings. And that's very useful when trying to do things that are a little bit more surgical, like recording a particular function or recording a particular sequence. And using some combination of those, you can enable automation and things like recording at boot time, for example. So in this case, we're recording BGPD, and this particular failure is a crash. Again, it doesn't have to be a crash. It could be just some misbehavior or some dropped packet. And there are utilities within LiveRecorder to allow you to identify those. In this case, it's a crash, and it's a security failure where a particular bad packet gets sent to BGPD, causing it to crash. So script, and it basically start the daemon, it'll run, and then it'll get a bad packet and it'll crash. So I've saved a previous run and loaded it in Qt Creator. I'm going to show you just something a little bit different, particularly, but it's the same debugger underneath the hood. So first, I've already loaded the recording file. I'm going to continue to the end and hit that sig abort. I can see my stack down here. I can see my local variables at the top right. And that's why I enjoy using this GUI. So I can see that there's a malloc print error over there, and that looks like a good point to go to. So I'm going to reverse finish or reverse step out to that point in time. And I can see here there's this malloc print error. So something went wrong over here. I'm going to look at my local variables, and something does kind of catch my eye over here, and that's there's this victim pointer to struct, and it's not byte aligned, and I would expect it to be byte aligned. So that looks like an interesting point to track from. So I'm going to go back and see where victim came from. And I can see here, if I look at my source code, that I'm in some error handling code. So I'm going to step out of that. And as I do so, you'll notice something interesting. You'll see that some variables get optimized out and then reappear. And that's because in a core dump, I'm basically capturing a snapshot of my process at that one point in time where a variable may have been optimized out. A recording file is conceptually similar to a snapshot of your process at every point in time. Basically, a recording file allows you to recreate that. So when I move around in a recording file, something may be optimized at one point in time, but all I need to do is go back a few instructions and it will reappear. So I can see that victim has reappeared. Now I'm going to see where victim came from. I can see victim comes from PP, which comes from this atomic compare and exchange. So I'm going to set a breakpoint on FB and go back to when it was set. And let's take a look at that. And I can see FB, FD has that strange value. I know a little bit about atomic compare exchange, and I can say that it passed the second argument to the first. So I can say victim FD is getting passed in to FB. So I'm going to see where victim FD came from. And I'm going to set a breakpoint at that pointer. I no longer need the previous breakpoint. And I'm going to, again, reverse continue and see when it was set. So a lot of flexibility in going backwards and seeing where things were set, which comes in handy when I find myself in what appears to be a free function. So I'm actually going to reverse step out and take a higher level look. But this looks like it's doing some sort of free. And I can see that I'm in this BGP attribute flush on attribute. So at this point, this is kind of where knowing the code lets me figure this out pretty fast. So with a bit of code inspection, I can even reverse step back into BGP attribute uninterned sub, and I can see where it does a free in this one, and that will let me know that it's a double free. Alternatively, I could set a watch point on attribute, and I can then see that there are two deallocations on it. Without an allocation, I can then recognize that it's a double free. And indeed, if you go to this particular CVE, you'll see that it's a double free. So being able to, again, same concept of being able to look at the state of the program and then examine the state as it changes. This means that if there's a particular section, if I have a stack corruption, I can set a watch point on that memory and then reverse continue to it, and I solve the problem. There's no issue with monitoring different threads. So one thread is overriding that memory, and I'm in thread 2 and thread 1 is overriding it, I can set that watch point in memory and go back, and even if it's written in another thread, I will see it there. So I'm basically able to examine the program at any point in time and reach back and find out what went wrong. I'd love to show some other features that perhaps could be shown in a future meeting. There are some features like multi-process correlation, which allow you to examine how one process is affecting changes in another process. It uses shared memory tracking, so it can show you when one process wrote shared memory, when the other process read shared memory. There are things like post-failure logging, which allow you to generate log files from recordings for cases when using a recording is not possible, but you want to generate multiple log files, or where it's costly to generate log files by rerunning the test several times. There's things like a log jump for correlating log files with recordings, and that comes in pretty handy when you have an infrastructure in place to monitor, when packets are being dropped, and you already know when a packet is dropped, so you can just jump to a point in time when recording and I've used that in the past to solve bugs in 15 minutes just by jumping to the point in time where the packet was dropped and seeing why it was so. So that's the demo. There's obviously a lot more to show and a lot more to talk about. I hope we'll have the opportunity to do that. Back to you, Stephen.
Thanks, Mohammed. So let's get back to our presentation here. Okay. This is kind of the point where a lot of people will begin asking themselves, will this work in my environment? You probably have a lot of questions around how much memory does it take? How big is the recording file? How much is the CPU overhead? And we have some answers for those, but it really depends upon your code and your environment. And we're happy to go into those details in a more, I guess, intimate setting where we can have that dialogue with you. But the best way to answer a lot of these questions of will it work in my environment is going through what we call the bug hunt process. And that's where we work with you. We do most of the work to set up Undo's LiveRecorder in your environment. And then we go chase some bugs together, similar to what we described with our telecom customers. I will say that every one of our customers that we've worked with in the beginning has had these doubts because some of this technology seems kind of magical, frankly. But again, happy to talk about how it works under the hood and show it in your environment. Once we get to the point where we're hunting bugs, typically a lot of these concerns just disappear because now people have shown to them for themselves, hey, I can hunt bugs 10 times faster, like all of these other telecom database, EDA, and other customers have been able to do. So the process in a nutshell is described here. The first meeting we would have would be what we call a whiteboard session. That's where we get our engineers together with yours to better understand your environment, your code, your build setup, and begin to work on integrating this into your environment. While we're doing that integration in the background, you could work with somebody like Mohammed to do a hands-on clinic or a sandbox exercise so that you can understand even more of the features of our technology. And then we conclude that with what we call a bug hunt. And that's where we, as I described before, we'll chase some known bugs that you have reproducers for, and maybe even some unknown bugs that you haven't solved yet, depending on what your criteria is. And then from there, of course, we can talk about how to get this into your environment on a longer term basis. I did want to touch on what we call the maturity model, and this is the view of over time how to deploy our technology. And the reason I want to mention this is a lot of people also have the thought in the beginning, hey, I've got these defects that are only reproducible out in the field. I really want to use this there. And what we recommend is using this in development in the beginning and gradually integrating our technology further in with yours. It's not a lot of work, but it does take some time, tweak it for your environment, and ultimately get to the point where it can be deployed out in the field if you so desire. So again, just that recommendation. Let's start out with the easier to solve cases in your development environment, gradually integrate in with QA, and then eventually gradually integrate in with your deployed product. So that's our recommendation about how to deploy ultimately. And what our recommendations, Mohammed and myself, have for how do we work together? Well, just a reminder, our technology has been proven with multiple Fortune 100 customers for over 5 years. That includes the largest network operating system in Silicon Valley, representing over 100 million lines of code, Juniper, and other networking customers. It includes the three largest, or two of the three, I should say, largest database vendors, SAP, included in that. It includes the top 4 EDA companies. I've mentioned most of those, and a lot of other customers in various other markets, such as enterprise, military, and aerospace, and others. Just a reminder, the typical results is our customers use a benchmark internally of 10 times faster debugging. Even for quote unquote mundane unit tests early in the development cycle, our customers usually experience resolving those about 2 to 4 times faster. And it's been proven for all classes of defects, all types of architectures, whether it's multi-process, shared memory, lots of threads. It works in all of those environments, both on hardware and virtualized platforms. And we've been able to work with these customers to reduce their mean time to resolution throughout their development lifecycle. So if that is of interest and you want to discuss this further, we recommend the best next step is to engage in the bug hunt process. And we can have a meeting to discuss it further, demonstrate our technology live to perhaps a broader audience, and then determine if you want to work with us to try and achieve those benefits. I want to conclude with this reminder. With our largest networking customer in Silicon Valley, we took a bug that took them 5 years to solve, recorded it, handed it off to one of our engineers, and an undo engineer was able to solve that in 3 hours. They're not all going to be that dramatic, but that is the potential of our technologies to solve things far, far faster than in the past. So we hope to be able to work with you to achieve that as well. And with that, how to get in touch with us. You can reach out to either Mohammed or myself. We'll leave you with our contact information here, and we hope to be talking to you soon. Thanks a lot.
Thank you.